Namaste and welcome everybody to the Transitional Artificial Intelligence Research Group, our TAI seminar series. This week we have Amuchi Ibenegu from our university. She's a PhD student and she's finishing her 1 year of a PhD kind of this week or next week. And Amuchi has done wonderful work in the area of bluebottle research. She has used machine learning methods to model marine stinger beaching prediction, also known as bluebottles. So I'll let Amuchi take the floor and present. Thanks, Amuchi.
All right, thank you everyone, and welcome to today's seminar. Thank you so much, Dr. Rohit, for the introduction. My name is Amuche Ibenebu, as was introduced, and together with Dr. Rohit, who is my main supervisor, and Pierre and Amandine, we were able to work on this project called, we titled a machine learning framework for handling unreliable abscess level and class imbalance in marine steam gap teaching prediction. These are some of the people that I call out, like they are part of the where we belong to, the groups we belong to. And this was supposed to be February 12th because I was supposed to present on January 15th, but it was February 12th. So we picked the project. So these are some of the table of contents we are going to present here. We're going to talk about the bluebottle teaching and steam, talk about introduction, and the rest of them. So first of all, when you look into this picture, you could see what is bluebottle itself. Most of us see these on the beach. These are like bluebottle in the water, and this is like bluebottle beaching, where they're like pushed off the ashore of the beach. And then this we know we have two types of bluebottle, we have left-handed and right-handed. So left-handed, depending on where you are, where the wind blows. If you are left-handed, it carries it towards the left, and you're right-handed, depending on where the wind direction is coming out from. So that is why this picture is showing you left-handed and right-handed bluebottle. And we have different types of them. But the truth of the matter is that they usually like call them Physalia species, family of Physalia species. So bluebottle is like from the family of Physalia species, and they are marine stingers. Sometimes they look like jellyfish, and we found them in Australian beaches and some other places. They pose serious significant risks to people and lives as well. Though we don't seldom have them result in death, but we can always have them result in some of health challenges like cardiovascular issues. If you have cardiovascular issues, it can become worse issue when you get torn from them. So it can lead to some cardio-neurological and allergy reaction, depending on your existing health issue. You don't know what the reaction will be on you. These organisms, they don't swim, but we found them in the beach. So how did they arrive to the beaches? How did they get to the beach? How do we find them to the beach? So it's something that requires serious attention. So Bong et al. 2022 indicated that bluebottle is, hold on just a few minutes. Bluebottle is found in the beach, but they are being derived by wind. So based on what they ascertained using statistical analysis, they carried out this result. We are trying to find out, using machine learning, the factors that also move this organism to the beach. So on this note, we are trying to now check if a prediction can be made. And based on that, we are doing this project. All right. So these organisms, like we are trying to, based on Brown et al., who indicated that wind direction and ocean current are major factors that take them to the beach. So they applied some statistical method to be able to like ascertain this. And then we are now trying to employ machine learning models to investigate what they got, if it is really in line with that, and to check if a prediction can be made based on this. So The data sets we are using in this place, these are like data description of what we are using here. So first of all, we got this data through the help of Dr. Amandine, who is in charge of this project in the Eastern Australia. And she's in our school, and the help of Daniel, who was a postdoc during then. So before we started this data set, we have like 14 attributes, which are listed here. And then we have to look into these attributes to check them. And we had 9 categorical, 5 numerical variables before we process them. Then this is really a classification problem because we are dealing with presence and absence. And then we are determining the presence of the blue bottle. We have a total of 3,851 samples. And this is the map of the east of Australian beaches that we are considering. We had 3 beaches we considered, and because the data set is from a Randwick Council report. So we had these 3 beaches we were considering: the Clovelly Beach, the Coogee Beach, and the Maribor Beach. When you look at the map of this beach, you could see that they are like the eastern side of the Australia, Sydney. So the Maribor is monitored year-round, and data is available from January to December for them. Then similarly, Coogee Beach has all year round, whereas Clovelly Beach, we had observation only September to April. So there is limited activity on Clovelly Beach during winter, Australian winter side. So this is like the technical framework of what we implemented in this data set. So I'm going to explain the bulk of everything we're going to like run down. So we had like data acquisition, which is the blue bottle gotten from blue bottle beaching. And then we had exploratory data analysis. It's always good to explore the data to see the behavior of these organisms, to see how they are, to know what we are dealing with. And then from this exploratory data analysis, we could be able to do feature selection. And then we modeled this data without data augmentation because we had some challenges in the data set. And we now applied some data augmentation techniques, something like class imbalance. We applied SMOTE, we applied random sampling. And then we also treated a case of synthetic negative approach where we used CTGAN. And then we also tried one SVM, which is still under the synthetic approach. And then we have 3 machine learning models we implemented: MLP, which is neural network, random forest, and SGB. So we tried 1 neural network and 2 resembling learning method. We applied for visualization case because of the nature of the behavior of the data set we are dealing with. So we have to look into the visualization to know if the techniques or whatever we implemented was able to progress the results. So these are like the behavior of this data based on exploratory data analysis. We could look into SST. Yeah, it's looking a little bit like Gaussian distribution. And you could see that this current distribution, current speed is skewed to the right. And current direction is looking a bit like bimodal because it is a secular data. So the data has a lot of issues because we deal with the secular nature of the data. So it's not linear, it's non-linear data set. And then you could see wind speed is also moving towards the right. It's like skewed to the right, similar to wind direction and current direction are secular data sets. So we had a correlation plot carried out on the continuous data sets. So when we look into this, we're trying to check if there is a relationship between them, a strong correlation among them, so that we can avoid multicollinearity. And when we looked into this, we couldn't find any correlation, strong correlation among these data sets. So in other words, all the continuous variables we had was okay for us to go for the data set. So we inferred into the data set the class distribution of the data of the output. We are trying to check if this is having a class balance set, because when you deal with classification, you need to check whether they are balanced so that there is no biasness on the result of what you're generating. And you could see that we are dealing with 94 against 6%. So that is an extreme case of class imbalance that we are dealing with here. So we inferred into the beaches to know if these beaches, the class imbalance, if it is across the 3 beaches we are dealing with. And you could see that the class imbalance is across the 3 beaches. So you could see each and every one of these beaches was dealing with class imbalance. So the problem affected them. So based on this, we cannot use accuracy as a metric for us to determine if our model is doing well if we are looking on the model. So another issue to identify here, aside the class imbalance, we have talked about class imbalance. This is a pair plot. When you look into the pair plot of the continuous data set, you could see that there is no clear line of decision boundary. That's looking on the left side of the plot. That is where we have the data set we are working on. Okay, for instance, let's look at the data set, the plot on the right side where you are dealing with breast cancer data set. You could see there is a class imbalance data set, but the orange is more than the blue. But there is a clear decision line between them. You could see that there's something dividing them, separating them together. So each and every one of them is different from the other. But when you compare to our data set, they are all mixed together. What is this trying to tell us? That at the same time, absences, under the same condition, absence exists. Under that same condition, presence exists. And this is a very serious problem. So we are dealing in this data set, problem of extreme class imbalance, problem of class overlap. That is two cases identified. So we checked in the seasonality of this blue bottle, which has already been determined. Like we looked into it and we put fair that there are more occurrences in Marubra, which is showing up there. And then during the month of February, over there are more occurrences. So Clovery Bridge is sampled from September to or April, like I stated. So it's understandable why there are no much data. So, and the blue bottle is frequently like experience from here. You could see that experience them more from September till April. That during May and August, we don't tend to like get occurrences of them like the rest of them. So in other words, during the Australian winter season, they tend not to like really occur. So we now went ahead to still model this data after all this to see what the behavior will be like. And crazily, we looked into let's look into the accuracy. And you could see that it's 0.9, but that's deceitful. If you say like your accuracy is high, that's a deceitful result because we're dealing with a extreme case of class imbalance. Now let's look into the F-score, which is where you're supposed to look at what your result is really generating, how the true positive and negative are really classified. You could see that MLP is having a 0.003, very, very poor for all the three models. None of them is even getting up to 0.5 or 0.3. So, which is a serious issue. Most class imbalance problem, because I modeled the class imbalance with the breast cancer, I was getting 0.8 even with the class imbalance. And what could be this problem? Because of the class overlap. There is no decision line. These models cannot determine which is which, so it's causing a serious problem. Now, if you look into the classification report, like you could see here, now, the classification report, let's look into the test. You look at the test class 0, that is the absence. You see that this model is automatically seeing the precision, the recall, and S4 are very high. But when you look into the class 1, MLP did not even recognize any of the presence class, and similar to random forest, because random forest is really like an ensemble learning model, is ensemble learning. Random forest and XGBoost tried their best, but their best was not enough because they could only do what they could do, but the data was not really behaving how it should behave, but data is still data. So we said, okay, because let's look into the true positive class, negative, true positive, true negative, and false negative, because these are what generates our F-score. How is it really classifying this absence and presence? And when you look into it, you could see that MLP could not even classify one single presence, could not even recognize any presence from the data. Random forest, because of the power ensemble learning power it has, the same as XGBoost. Random forest was able to classify 8, and XGBoost couldn't classify 4 because of their power. But you could see how poor. Out of the whole data set, they could only recognize 8. That's a really very poor performance. So in other words, you realize the effect of this class imbalance and class overlap on this data set. Now, we now look for solution to this problem. How do we solve this? Because it's a serious problem. This is not something to present out there that you could use to talk about what your data is doing. So we went, there are a series of cases. Let's solve the problem of class imbalance and know maybe class imbalance could improve our result. And we look into cases of what if this data set, this absence data is really unreliable? What if this absence we are dealing with When we talk about unreliable, we are not saying that they are not existing. It's existing, but they are not unreliable for this prediction. Why? Because there are factors. I'm going to give an example. If, for instance, I come to this place I am, I got stung, I got bitten by a snake today, and tomorrow I come back, somebody comes back under the same location, and that person doesn't, you won't see that snake tomorrow getting that case. So it's not a case of whereby issues you want to be ascertained that this, for these particular occasions or time, we're expecting absence. No. There are other factors that determine the absence of bluebottle. There are cases of their biological life cycle. There are cases of because they are blown ashore, that is how the data was gotten, blown ashore based on bleaching. We don't know the number of days they are still in the ocean before they are blown outside. So those factors were not considered, and it's hard for it to be considered. So we looked into balancing this data, which we know about SMOTE is used major techniques for balancing of data set. We looked at Young provide a method. So we are looking, since this data is unreliable. Okay, for instance, let's assume we don't have this absence. What do we do when we don't have an absence data set? So we look cases where they are now treating results like there is no absence data. So Young et al. Combined generative advanced network, which we call GAN, with long stem and try to generate synthetic negative data for a financial data set that was lacking. So the GAN focused on mimicking the original data set, while the LSTM focuses on the temporal dependency. But we are not looking into the temporal dependency of this data set here. So in that case, we considered only the GAN. So we looked into the hack et al., who also tried to model one class support SVM. Using one support SVM, you only model the positive class and then generated a negative sample to test alongside the positive class. So we considered these three approaches to see whether we are going to also have an issue. We also look an improvement. We also looked into the case of random sample. Oh, let's randomly sample from this data set. Because what if some of the absence data sets we have in there are just all noise? What if they are noise? Random sample could help us look into whether they are all noise. So these are some of the approaches we implemented. So now after all this into the SMOTE, you could look after we apply SMOTE. SMOTE was able to balance these data sets. But SMOTE did not improve that result. When we look at the F-score, it was 0.17. No much improvement. You only improve it a little bit. Now, based on the random sampling, random sampling is now trying to tell you that most of these absence data could even be noise. So when we look at the MLP random forest XGBoost based on random sampling, you see that it went to 0.6. It improved to 0.7. It improved to 0.7. What is this trying to tell you? Obviously, the absence data is the problem we are dealing with in the data set. So the variabilities among these absence aren't much. So there is no variability. So most of them could be noise. They could be the same thing. So it's automatically generating noise. So we now look in the synthetic approaches we implemented. Based on this synthetic negative approach, which is the GAN, we see that the result was really very okay. It went to 0.7. It went to 0.77 and 0.6. Also, the one class SVM tried these bets based on the F score. Even if we look at the AUC score, they are really very high, even the synthetic approach. So one class SVM also tried, but SMOTE, which is a popular a popular method for class imbalance, was still very poor. So in other words, the problem was not really class imbalance. The problem is beyond class imbalance. The problem of the data set has nothing to do with class imbalance. SMOTE can only balance or didn't solve the problem. So it's beyond class imbalance problem. It's a problem where the absence is really unreliable, and most of the absence data are really noise to the data set. So okay, we now also looked into the accuracy, the true positive, negative confusion matrix of this data set. When looking into them, you could now see that ML could properly classify more of the presence. XGBoost could also classify more. Random forest could classify more. So from this, you could see that initially the variability of the class overlap, the issues in the data set was making them more to clearly get a decision line. Now remember, when we use gang is going to mimic the result. They're going to see what gang did after that. So now, based on the data generated from gang, we said let's infer to see the behavior if gang did a good work in mimicking the existing one but trying to get the result. So if you look at the this is the distribution of we looked into the secular behavior because that is the most important one. So even know if the secular nature is properly like got in the way it is like, you could see that he was able to mimic them. This is the actual before, and this is the present. So this is the actual of the wind direction, of the current direction, and this is the synthetic of the current direction. Yes, he was able to make sure that it is within that range of 0.0 degrees to 45 degrees that the current direction happens. That was able to give us the same generation, similar to the wind direction and current direction. Though there are variabilities, but he was able to like did a good work in trying to mimic it. Now we looked into the precision recall visualization of these data sets we have gotten and worked on. Before we did the augmentation, this is the precision. The train was 1, but you could see the test is not moving anyway. It's almost like flat down line. And similar to when smooth and the no augmentation, no difference. They are like similar to the same result. But when we try the random Oversampling approach, you could see how it went up. The precision, they are doing very well in precision and recall. And now this is this non-negative approach, synthetic approach. You could see them moving towards one, and they're all going almost in the same direction. Now, we also looked at PCA. Okay, this PCA, let's check if the PCA we're having is really like, is there clusters? Are they now becoming clusters or result generated? So this is the no augmentation techniques. You could see that these are all mixed in, no any clear or any simple clusters you could see within them. Similar to smooth, because smooth is just going to do exactly the same thing and give you just expand more of the result using the nearest neighbors. Now, the random sampling could show us some clusters within here. You can see small clusters around there, even though there are little scattered of the blues, but you could see that there are some clusters in between compared to when we had the other one that everything is all packed in the other. And then with the synthetic data, even if there is no cluster, you could see clear line of cluster here, clear line of cluster here, clear line of cluster here. So you see that there we are now. So if you check this into a pair plot, you could see maybe some decision line being showing that the class overlap issue has been solved to a certain extent. Now, using random forest, we wanted to like look which of the direction, what are the factors that contribute this organism to the beaches, that derive them to the beaches. And then this was when we had the actual data set. It was showing that wind direction is a major factor. And then when we implemented SMOTE, it was still showing us that wind direction is a major factor. Now, when we did random, this is when we had synthetic data sets. It was showing us that wind direction and current direction are like the two. This is not ascertaining what Bronk said. Bronk et al. That told us that current direction and wind direction are like major factors that derive this organism to the beach. And now we said, okay, let's discretize this data set to say we already know that wind direction and current direction are factors that derive them to the beach. What side of the wind direction brings them more to the beach? So we discretize them, and we could see that when the wind is coming from the north and south, in the month of February, we have high chance of having this bluebottle to the beach. So we now looked into the pair plot. So this is now the pair plot of the city gang compared to the previous one where everything was in between each other. You could see some of them outside here, some of them like outside, which is now a little bit easy for the model to be able to make some decision compared to before when everything was just all inside, no a little bit of separation or something. But in this case, you could see some the blue are a little bit out and the orange are like out as well. So you could see like the GAN was able to help to create a decision line. Now, in conclusion, the commonly used data augmentation technique SMOTE was ineffective in addressing the class overlap and the unreliability of the data set. He was able to balance the data set, but wasn't able to solve the problem of class imbalance. So when we are dealing with class overlap, SMOTE is not an option to deal with. You have to look for the root. In contrast, the synthetic approach and the random undersampling approach successfully managed both the class overlap, the class imbalance, and the unreliable negativity of the data. And then we identify wind direction, particularly from the north, south, as a primary factor influencing bluebottle migration. And then during February, when the sea surface temperature is very high, there is a high chance of bluebottle. So when you like going to the beach and you look at your forecast and it's in February, just be sure that there is high chance of you seeing a bluebottle. So be alert to avoid getting stung. Then, however, to improve the accuracy of prediction regarding bluebottle presence, incorporating the temporal and spatial pattern could help us address the lack of understanding. And then we could look into the population dynamics and life cycle that will help us now be ascertained that these absent data we are doing now are now reliable. So these are some of the references I have like worked with as well. All thanks to Rohit, Pierre, Amadine, and Daniel, which make this stressful data and frustrating data effective to this result. Thank you. This is like the GitHub. I'm gonna like show my code, the GitHub code. I'm gonna stop sharing. I'm gonna come back to all the data sets we use here. You could see the CTCAN generated data sets. This one is from Bluebottle sample data, like when we did random sampling to generate the data set. And then this is after pre-processing, and then the random is the initial data set used. So we had the initial data set, and then from this initial data set, we now pre-process, clean the data, which resulted to this model data set. And then from this, we had a CTCAN and the random data set. So then the models we did with, this is CTCAN for SVM, when we had to deal with one class SVM, negative class. And then this is when we did exploratory data analysis. All the stuff we got is all over here. Okay, when we did discretizing of the data set. So this is how we discretize data, turning them into discretes to be able to get the units of each and every one of them. So, and then this is the whole model, everything from this, everything you want for the model, the whole 3 techniques we tried. So we are all incorporated in this one. All of them are here. So the packages implemented is here. Thanks to Arvit, who taught me how to arrange packages and then put it into this, and then was able to have this. And we have the plots. For instance, this is current direction plots. You could see them. These are some of the plots we generated from the data set. So this is the GitHub. Thank you.
Thank you, Amuchi, and it's an excellent presentation. Thanks for sharing the data set. Now we'll take questions from the floor. Yep. Any questions from the room out there?
I do have a question.
Right.
Thank you, Amuchi. It was really nice presentation and great work, especially for just 1 year. Congrats. So my question, first one is, maybe you mentioned it and I missed it. What was the feature that you have used for your model, except for the wind, wave, and currents? I want to see if you have included latitude and longitude and also time as input for your model or not.
No, I didn't. Thank you for that question. So we didn't use longitude and latitude because it's gonna be categorized. It's just strictly from each of them is just strictly from the three beaches. So it's more like you're gonna categorize them 0, 1, 2. And then because we are not looking into the spatial temporal data set, it's more like a category. If I was dealing with the spatial temporal nature, I'll use the latitude and longitude, but I didn't implement it here. So it's more like based on this feature attribute, when we did the coloration, I was supposed to show you the categorical coloration, which was not presented here. When we did them, we found out that most of them, latitude, longitude, orientation, so all of them were strongly correlated to the beach. So there is no need of modeling with the beach and the latitude and the longitude. So that would be a strong, and they were like 1. Their coloration was 1. So there was no need to model with them since I was not dealing with the spatial temporal nature. But concentration was like on the beach and then attributes. So the 5 major data sets attributes I use in this data set. We are the sea surface temperature, current speed, current direction, wind direction, and wind speed. And then we did with attribute. Every other thing you see here are correlated to the beach or correlated to council reports. So I didn't work with that.
Yeah, amazing. But the point about the geodata is that there's a correlation between a spatial correlation and also a temporal correlation. So each beach is kind of affected by the beach next to it. So there should be a way to connect this data set to each other. Also, when you're dividing the data set to train and test, did you do a random split or did you consider?
Random split of 60 to 40. Sorry, I forgot to say that. What's the random split?
Yeah, it's also good to consider something like checkerboard, not to bias the model to some, like for training, when you use the randomly split the data, it will be biased, might be biased to one location, but there are some methods like checkerboard, which is used for geodata when you split the data into train and test. So it will consider. Sorry?
I didn't get your question.
So when you're working with geodata,
Okay.
when for splitting the data into train and test, it's nice to use some methods like checkerboard, not to help the model not to bias to a specific location for train and a specific location for test. So it is a good thing to consider. And yeah.
But that shouldn't be the case where you are dealing with your concentration is looking into the spatial temporal nature of the data set. I feel like that might be where that particular case you're talking about comes in. But in this case, we are trying to like automatically solve the problem of the data first. Then it could be extended. That's why I said it on the last point. It will be necessary to incorporate the spatial and temporal nature of this data set. So if we are looking at expanding into the spatial temporal nature, that could be a very good idea. Thank you for that section.
Yeah, not a problem. Awesome.
Okay, thank you, Mandana and Amuchi. We have another question. Anybody else has another question? Um, Anybody else? No. So I just also want to comment on it. I mean, the data set. Yes, we have not taken the latitude and longitude into account, spatio-temporal data. But I mean, if you use the latitude and longitude, basically you are trying to restrict your model to different latitude bands. So that's one problem. The other thing is like we'd like to predict the presence or absence of blue bottle irrespective of where the geolocation is. So that's the other that's the other reason we don't want to include that. But so there's the thing is the geolocation is dependent, the temperature, the sea surface temperature, the weather, the climate conditions, that kind of are correlated to the geolocation. So we are in a way taking those things into account. But it's a it's quite a complicated data set in the sense what is absence. So I would like to ask Amochi to go back to her slides on the slides where she showed things about PCI. I think Amochi, you need a little bit more. Can you give us some more information why you used PCA, because I think it was a bit rushed in the presentation.
Okay.
Yeah, just
Yeah.
shortly comment on your the problem, Rohit. So the point is that because it needs different level of simplification, right? But the point is that we are trying to ignore the special correlation. But point is that when one beach at this location is the presence and absence of the blue bottle on one location is actually have an impact in the beach next to it. So they have some kind of correlation between them when they are like the closest beach to one, the prediction for this location, the closest beach are actually near the prediction for those one are close to this one. So in real world, there is a correlation between them. For simplification, we ignore
Uh,
that, but in real
I
world,
mean,
there
it
is.
is like you would have to explore the data. Perhaps you can do it as an extension of the work where you review the data again and show if there's correlation amongst the beaches, because these beaches that we are looking at are very close in distance. If you looked at beaches in some other states, maybe then the climate data, the sea surface temperature, wind intensity, other things, there would be more variations in it. But here we are looking at beaches which are within 10 kilometers of each other. So that's the thing to note there. I mean, you've got a valid point, but and you may end up finding no correlation for that reason because they are
Yeah.
too close. So, if you could explain why you used PCI.
Oh, okay. Because of the class overlap in the data set. So in the beginning, I showed you the issue of the class overlap and why we are trying to show you that this absence data is really unreliable for this. Because in the beginning, if you look at this without no augmentation, you could see that there are no clusters among, like the the reds are not clustered together, the blues are all scattered everywhere. They're like just mixed interwoven within each other. And similar to that, we're just trying to check, infer into this, could there be clusters? You know, when there are clusters, it shows that there could be a clear line of decision boundary. So when we inferred into this visualization, we look into the SMOTE. When the SMOTE generated, there was no difference between SMOTE and the no augmentation. There are no clusters. They are just moving between each other. They are on top of each other. Even if you try the kernel piece A, the one that considered the secular behavior or non-linearity PCA, you could see also, we even looked into if we reduce the dimensions of some of these things, could there be still the cluster or could there be any separation? So even with dimension reduction, there was no difference in the data sets without augmentation and even with SMOTE. But when we apply random sampling, the approaches and the synthetic approaches, you could see that after the reduction, there are some clusters in each of them. Though it compared to the previous one, though it's not too much, but it's some progress. Like you could see here, there are clusters, so that means reduction was able to help us infer into this data set that there were some clear line of decision boundaries from the new data set in general. Yeah.
Okay, thank you, Amochi. I just also want to note the thing about no negative data and unreliable negative data. That's a major theme of the paper, and we've had discussions about this for a while. So, this is firstly to call something unreliable, you need to show evidence, right? And I think if you can share the results again in the table results, There we have the case where if you take the data into account, then your model is basically not working well. So the data that you have, the negative data that you have, is unreliable in the sense. But the problem can be sorted. Let's say that so there are two things, right? You have like you could have reliable negative data, but you have a class imbalance problem,
Yes.
right? So you
Yeah.
address that class imbalance through the data augmentation methods, which you have done here with
Yes.
SMOTE random sampling. And you found that that is not good enough to
Yes.
address the problem. And why do species such as blue bottles move in this manner? And if we can see, we've done used a random forests to see the feature importance, and it shows some attributes are more important than others. But not all data sets are I mean, you cannot use machine learning for everything. Okay, so I mean, although I am like one of the key authors of this paper and behind the experiment design and all that, I think this is a classic example where machine learning cannot be used for predictions. It is where machine learning can be used for understanding the behavior
Behave.
of the phenomena or the species. So that's what it is being used for. But it's not, we are not giving out a software package out there that you use this and it will tell you when blue bottles are going to migrate. We are just saying that, okay, there are some features. If you could go to the slide showing the feature importance, uh, that based on some of those features, maybe there's more chances of blue bottle beaching. That's all we are trying to say here. And the wind direction is a major thing, and it's kind of quite obvious. And also sea surface temperature, right? It's like
Yeah.
whole machine learning is basically affirming, reaffirming what is obvious out there. You have blue bottles, you see the physiological behavior, the way they are. It's basically jellyfish type of species, just is hanging on the surface. They're not really swimming much. And of course, when you'll have a strong wind direction, they are going to be kind of blown in that direction. So that's one thing, right? The other thing is like their species, in before some major events, like you have a tsunami, you have an earthquake. Some of the animals, they just run to higher ground without somebody telling them, basically, right? So you have some natural phenomena that are not really fully explained by data, and that happens. And there are some big open questions in nature. So also, like, how do birds navigate all around the world? Eagles, how do they fly and navigate? How do sharks, whales, they navigate? There are some ocean currents they follow. There may be some electromagnetic spectrum, some other things, magnetic fluctuations, some other things which we are not recording, or maybe our science so far, although we have gone into AI and robotics, but there are other things in nature that we are not fully kind of recording in data to really understand the behavior of a species moving. So I want to just say that the data is very limited. It's just presence, absence of blue bottles, and just based on some weather, climate conditions, very external condition, nothing to do with the biology or the behavior or the magnetic flux, so the electromagnetic changes, or could be some solar changes, radiation changes, solar radiation, sunspots. There could be many factors, but based on what we have is this research is reaffirming this. And I think machine learning has a long way to go, and the data is not really that reliable. So we're just highlighting with this research that unreliable data is a thing out there, and when that thing is there, then it's hard for machine learning models to do things. So that kind of brings us to the end. If anybody has any questions or comments, we can take one final thing. One question, final question or comment. Okay. Thank you very much, Amuchi. This was an excellent presentation, and I'm also missing my physical presence there, which I should be there. But anyways, we'll continue with other presentations in the coming weeks. Thank you, everyone.
Thank you. Bye-bye. Thank you.